Hi, my name is Harvey Molino, and I'm one of the instructors that teach the John M. Campbell G4 Gas Conditioning and Processing course. Over the next 10 weeks, I'm going to show you various bits and pieces of what we cover in the G4 course. Today, I'm going to start on phase envelopes. Phase envelopes is Chapter 4, and what we typically cover in this chapter is shown on the screen. During this chapter, what you will be able to do at the completion of the session is to analyze pure component phase behavior, analyze multi-component phase behavior, describe the benefits of transportation of fluids in the dense phase, discuss the effect of heavy end characterization on the shape of the phase envelope, and also discuss the effect of various non-hydrocarbons on the shape of the phase envelope. Today, we are going to take a look at a particular segment, the multi-component phase envelopes, in detail. When you attend the G4 session, you will have in front of you two volumes. Volume 1 talks about the fundamentals of gas conditioning and processing, and Volume 2 talks about the equipment associated with the fundamentals that you will find in your facility. The purpose of a G4 session is to understand how changes in downstream and upstream operations will affect your facility. So in order to get a better feel for what's going on in the facility, we need to focus on fundamentals. We're going to talk about phase envelopes. On the diagram, you see a plot of pressure versus temperature. And what we show is a bubble point curve and a dew point curve. The two curves come together at the critical point. The critical point is that point where the properties of the liquid and the vapor are the same. If we go to our curve, in this region, you're going to have a liquid phase. In this region, you will have a vapor phase, and in between the phase envelope, you're going to have liquid plus vapor. We call this the bubble point curve because when you take a liquid and you heat it up at constant pressure, when you hit that curve, you form your first bubble of vapor. This temperature is the bubble point temperature at that pressure for this mixture. We call this the dew point curve. If you take a vapor and cool it down at constant pressure, when you hit that curve, you'll form your first drop of liquid. Continuing with the analysis of the phase envelope, we have a point on the phase envelope called a Crichton bar. The Crichton bar is the highest pressure at which two phases can exist. The Crichton is the highest temperature at which two phases can exist. You can draw a vertical tangent at the phase envelope to indicate the Crichton. You can draw a horizontal tangent on the phase envelope to indicate where the Crichton bar is. We have read lines which are called quality lines. Anywhere along these liquid quality lines, you will have a constant mole percent of liquid. So anywhere along, for instance, the 10% liquid line, I will have 10 mole percent liquid and 90 mole percent vapor. One of the things to notice on these quality lines is that they are not equidistant in the phase envelope. If you were to take a vertical tangent through all the quality lines and connect them, you would end up with a curve such as this, which defines the retrograde region. Retro means reverse, and grade means temperature. Very weird things happen in this region, and if you don't understand the retrograde region, you will have a great deal of difficulty trying to troubleshoot operations in your facility. Let's take the path that is shown over here on the diagram. If we start off on point A, which is a dense phase region, and we drop the pressure, as you drop the pressure and you hit point B, what's going to happen? You're going to hit the dew point line. And when you hit the dew point line, you're going to get your first drop of liquid. Now ask yourself, does that make a lot of sense? As you drop pressure, do you really expect liquids to form? It's not what instinctively we would expect, yet it happens. And if you continue to drop the pressure, you get deeper into the phase envelope and you drop out more liquids. Operators in facilities will be driven nuts if they do not have an understanding of what's going on in the phase envelope. Liquids are continuing to increase. Your liquid production increases as your pressure drop goes down, and this can cause great problems in operating equipment that is meant to see only vapor phase flow. When you finally get to point D on this diagram, you've reached this curve of maximum liquid production. As you go past point D, your liquids start to decrease until you finally hit the dew point curve where all your liquids disappear and now you are in the vapor phase. So understanding the phase envelope is very important to be able to troubleshoot facilities or equipment in your facility. Another item that is important to understand on the phase envelope is this Krikandentherm. Very often we specify hydrocarbon dew point specifications as a temperature spec only. So for instance, if my hydrocarbon dew point spec in this particular example happened to be -3 degrees, that would be what is called a Krikandentherm specification, since no pressure is given. So if my my Krikandentherm hydrocarbon dew point spec was -3 degrees, that's the point where the vertical tangent hits the temperature line. That's one common method of specifying the dew point requirement of a gas. So the Krikandentherm needs to be less than the hydrocarbon dew point specification. When you attend a G4 session, we get into the reasons behind that statement in great detail. The next time we see each other, we will be talking about hydrate formation temperature. Until then, I will see you at that time.